Good morning, all. Welcome to the day 4 session on the FDP on machine intelligence. Today's session will be on reinforcement learning algorithm, presented by Dr. Rama Subramaniam, Associate Professor of LIBA. I request our head HOD ma'am to introduce Dr. Rama Subramaniam.
So, good morning to one and all. On behalf of LICET, I welcome Dr. Rama Subramaniam to the Faculty Development Program on Machine Intelligence as the resource person for the forenoon session of today. So, let me introduce Dr. Rama Subramaniam to the participants. Dr. Rama Subramaniam is an associate professor in the Center of Logistics and Supply Chain Management at LIBA. He is a certified supply chain professional and also a ROC certified big data analyst. He is an alumnus of IISc Bangalore, and his areas of interest include logistics and supply chain management, data analytics and operations management. He has a fine blend of teaching, research and consulting experience. His consulting experience involves leading organizations such as Indian Flavors and Fragrances, OptiRisk India, CMC Limited, ATG Tires India, and TVS Logistics in the areas of supply chain management and analytics. He is also a visiting faculty at Malaysia Institute for Supply Chain Innovation, Malaysia, which is part of renowned MIT Boston's Global Scale Network. Dr. Rama Subramaniam has more than 30 publications in reputed journals and conferences. So we are really honored and privileged to have you amidst us today, sir. Thank you very much for accepting our invitation to conduct the forenoon session on reinforcement learning algorithms. Thank you very much, sir, and I request you to take over the session.
Good morning, all. Thank you very much, Mr. Balaji and Madam. Thank you so much for the introduction. Yeah, it's my pleasure and also honor to participate in this FDP on machine intelligence. Okay, so let us start the session now. I will share my screen. Is the screen visible?
Yes, sir.
Yes, sir.
Ma'am, are all the participants inside or should we have to wait?
We may go ahead, sir.
Yeah, let's go ahead. Okay,
Yeah.
great. So good morning, all of you. So it's very interesting to look at the structure of this faculty development program. Very interesting topic and also very contemporary, and that is something that is required for all the faculty members today who wants to take up on this area of data analytics. So I'm sure you must have gone through the basics of machine intelligence, starting from the statistics part in the previous 3 days of the workshop. Today's forenoon session is focused on this topic of reinforcement learning, which is a sort of standalone topic from the rest. So let's see how this topic can help us in developing AI systems and how this can be implemented for different applications. So today's session is going to be more a beginner kind of an exercise where I've sort of structured this into 2 sessions, where the first session will focus on a very rudimentary topic in reinforcement learning. And the second session will touch upon one of the algorithms of reinforcement learning. So the idea is to get you started into this particular topic. So for those of you who have not heard about this topic before, I'm sure this is a new one to look at. And also there could be confusion as to why there are so many different algorithms that are being covered in a workshop. So you might have heard about machine learning, supervised learning, unsupervised, and things like that, right? So where does reinforcement learning fit in the scheme of things? So that's what we are going to see today. So let's first see what is reinforcement learning and the basic idea behind RL, and also how is it different from the machine learning that you have already seen in the previous days. So let's start with the difference between the reinforcement learning and the machine learning. So I'm sure you must have worked on different data sets in the previous 3 days. They would fundamentally, if you look at them, they will use a sort of historical data for fitting a model. So when you want to fit a model, when you want to develop an algorithm, you have to use historical data for developing these models, right? And so typically this historical data would consist of a lot of independent variables and also a target variable. And this target variable is something that is used inside any of those machine learning algorithms, whether you take a decision tree algorithm or a random forest or even a neural network for that matter. All these have to take in what is called as the target variable. So the primary aspect of machine learning techniques is that they rely on the historical data, and specifically there is a target variable that guides how the models are being developed. And that's how they are getting also categorized into supervised, where the target variable is present. But then you also have another category called unsupervised, where the target variable is not present, but still you have the historical data on different independent variables. And then you apply algorithms like cluster analysis or even a PCA technique uh, to achieve different objectives. For example, PCA method could be used for reducing the amount of data or reducing the size of the data, whereas a cluster analysis could be used possibly to group the customers into different segments so that you can better position your products and services to their requirements. So that is about the unsupervised. So both the supervised technique and unsupervised technique, they rely on the historical data a lot, without which they cannot work. So if you look at the characteristic of machine learning, whatever I've discussed so far, these three aspects become very important. Now, if you look at what is this type of feedback that goes into the machine learning model, so how is that model is being developed? It's basically being developed by means of what is called as the instructive feedback. The instructive feedback is the way by which we give the information in terms of the target variable, and this target variable is used for building the model. So we sort of instruct this model on how they should be fitting the data, right? So that's the fundamental way in which the machine learning models also work. And then you also have what is called as the deep learning, which is an subset of your machine learning, where it uses the neural network and the advanced structures of the neural networks to learn from the data. And again, if you see deep learning also, if you notice, they rely on large volume of data, right? Large volume of data. So data forms an integral part of all this machine learning models. And that is where reinforcement learning comes in as a sort of a complementary algorithm or a complementary way of looking at things, where it learns by trial and error. So if you ask me, are there not going to be any Historical data as such, yes, I mean, we will have an historical data, but that is something that gets generated out of the experience that these methods are able to gather over a period of time. So when they start the learning, typically they start with no experience at all. And as the time progresses, you will see that these methods start to gather a lot of experience and starts to learn from them. And so that's the primary difference between a reinforcement learning and a machine learning model. So please note, this is the key difference that exists between the previous models that you have seen and the one that we are trying to see today, right? And so when we start with, we do not have any historical data, but as the time progresses, the algorithm is able to generate more historical data, which it uses for the learning purpose, right? And so the kind of feedback that goes into these models are called as the evaluative feedback. Now, what do you mean by evaluative feedback? Instead of saying that, okay, if I take the target variable, this is a particular value that you see for a given model. Here, we sort of give a feedback to the method saying, okay, you have reached this particular point, and so see, here is your uh, reward or your signal. So these are like, indirect means by which the algorithm is guided. So they are never part of your uh, direct learning process. And we will see how these are structured by means of a formal exercise. But then at this point of time, you can just assume that these methods are going to take up a kind of an evaluative feedback based on which they are going to revise their process and also the way by which they learn. And these are also generalizable for a particular class of problems, which need not be the case in the case of a machine learning model. So what I try to mean here is, if you develop a model for the machine learning, okay, given a data set, right? And if I change the data a little bit, these models tend to change. For instance, decision trees, if you take, they suffer from this problem, wherein if you change your data a little bit, it will result in a huge variance, and because of which uh, the answer is going to change, the accuracy of the model is going to change. But then if I look at an RL model, an equivalent model of an RL, they have the capability to be robust enough uh, to be applied for a specific class of problems. So if you are able to train your model on a specific set of data, then you could see that these methods or these models can be generalized for a specific class of problems. What do you mean by particular class or a specific class? Let's say if it's a robotic example where it's going to pick and place, then if I develop a RL model for that pick and place exercise, then this RL model can be used in a similar task. Instead of, let's say, a square object, if I replace it with a circular object, the robot could still possibly work and the task can be completed. So that's what I mean by generalizability. So given a specific class of problems, once you train a RL model on the data, and if it's able to learn from the experience, then it's very, very easy to generalize them. Now coming to this next slide, this one talks about deep reinforcement learning, which is again a subset of reinforcement learning class of models, and also overlaps with the machine learning. So this could confuse you a little bit because we just now saw that deep learning was part of the machine learning, and now we are talking about deep reinforcement learning, which is again a deep learning model. Okay, but then if you really see, the deep learning model plays a secondary role, although its role is very much required in terms of the learning activity. The reason why these deep learning models are now starting to be used inside the oral models is the requirement of the task. So you see, we have now variety of complex tasks to be completed. And for all these complex tasks, we can't use or we can't rely on a base or a basic reinforcement learning model, which could suffer from the scale issue and so many other things. So that's where the reinforcement learning can be combined with the deep learning. And so please keep this in mind. Even when we combine the deep learning model here, as I said, the role played by the deep learning model is more of a complementary or a supplementary role, whereas the actual action is taking place inside the RL method itself. Because the heart of the deep RL also lies in the oral techniques, which are allowed to learn from the experience. And the deep learning is now only going to help this reinforcement learning scale up to larger problems quite easily. And that's why I've put these examples here. If you look at this particular deep reinforcement learning models started coming in only after 2015, when DeepMind started pioneering this particular method. And there was a paper published from the Google team on the deep reinforcement learning, which was published in Nature journal, a well-known journal in the scientific community. And that is where they exploited the the uh, advantage of deep learning model, and they combined that with the powerful nature of the reinforcement learning models. So as you can see now, when we combine the oral and the deep learning model, you have a very powerful combination in hand, and it's very, very useful for solving very, very complex problems that one can come up. I've just given here a sample of different, applications which Google themselves developed, starting from the game of Go. So the Go is a game which is similar to, the chess game. Uh, all of you know what is chess, right? So it's basically a strategy game. So the Go game that you see here is a sort of a checkers. Everybody have seen checkers, right? So you can assume that this Go is nothing but uh, an extension of the checkers that we have seen and played in our early childhood, or possibly even now. So if you look at both chess and this game of Go, they both involve what is called as the strategy, right? What is common between them? So any chess players here? I'm sure many of you play chess, or at least played chess at some point of your life. Any active chess players in the community here? Okay, so no one wants to talk. So looks like I'm the only one who is going to talk for the next 2-3 hours. So please don't refrain yourself. It's a faculty program. So please feel free when I try to ask or when I request for a feedback, please feel free to give a feedback to me so that I can also know that you are present in the session. Right. So strategy is a very important component of the games. And so these two games were solved by the Google, in 2015. They tried to first develop a system for Go, and they called it as AlphaGo. So the name of the program that they developed was AlphaGo. And similarly, for the chess program, they developed what is called as the AlphaZero. And so these two games, which rely on the strategy part, exploit or can be an useful, grounding for applying the deep reinforcement learning problems. Now you also got not just the games, so don't think that orals are useful for games. But typically, if you look at the development of the field, it has started to come from there, because games provide a very constrained environment, very simplistic environment of real life. And so it's a test bed for all our scientists and scientific community to develop and advance their models. So although it may look like a very weird application of oral for solving games, but they are actually very, very difficult. People have started from two-dimensional games, these are so-called Atari games, which are quite popular for the earlier scientific researchers who use them for developing the RL algorithms, and we have grown from there. So we should not forget that point. So games provide a test bed for developing the RL models, and still you see any models that you develop, you can still look at solving the old two-dimensional games or even a 3D game to see how well your RL model that you have developed is able to perform. Because like I said earlier, the idea of developing an oral model is to solve a specific class of problems. So we are able to come up with a method that can solve a complex problem. Then it could be equivalently applied for a different application, but something that is quite similar to the developed one, right? So the protein folding example that you see here is the healthcare example. And this was solved pretty recently by the same DeepMind team, I think last year. So protein folding, if you go and search for the protein folding problem, you will see how complex it is. And this has been a long-standing unsolved problem, for a lot of decades. And all the doctors were very interested in cracking this. And so here comes Google, and they are able to now solve this protein folding problem using the RL technique. Now then you have not just the protein folding, since we are now, at least people in Chennai will know how reliant we are on the weather forecasting models. I can easily relate to 3 years, 4 years back, or at least before 2015, we never thought of using forecasting model to check for when a rain is supposed to come, right? So even today, before I left, I sort of checked what is going to be the weather for today and tomorrow. So that's how important weather is playing a role, because of the climate change and other things that are happening today. It becomes very important to study the application of all these models to forecast the weather, which is again a very, very complex exercise, right? And there are different models already in existence. There is an European model, there is a US model for forecasting the weather. But then now comes the Google DeepMind team, which are able to now develop a reinforcement learning model for forecasting the weather. And this is called as nowcasting. They call that as nowcasting, meaning the forecast is for the coming 5 or 10 minutes or possibly 1 hour. And that's the maximum time window for which it can predict. But then the accuracy of this method seemed to be very, very good compared to the existing forecasting models like GFS or ECMWF. So RL models are now, trying to take the role of all this complex simulations, and has a different approach to do the prediction part. So if you fundamentally look at all these existing forecasting models, they rely on complex physics and weather data to come up with a forecasting in the next 1 or 2 days, or even possibly 1 week. Whereas the RL technique is now going to rely just purely on all this data, but learns. So there is no historical data that is fed, but then it's made to learn from the existing ones, right? From the experience. So That's the application of RL models, right? And then apart from these two combinations of deep learning and your reinforcement learning models, you will also tend to see, another technique which is a quite popular one in the computer science field. It's called as Monte Carlo tree search algorithm. This is also typically used in all these complex models. So if you really look at the complex applications that are existing today, I would say it's a combination of tree search method. This is purely by means of how the learning has to progress. And the second, you have the deep learning model, which helps the oral model to learn. And on the top of it, you have the oral model, which tends to use both these methods to learn from the experience, right? So I'll take a pause here for a couple of minutes to take up any quick questions that we may have before we proceed further. Okay, no questions so far. Fine. Then let's go ahead to the next slide. Already talked to you on the applications of RL for the games. Right. But then you also have applications from the business side of it. In fact, one of the examples that I've taken for today's exercise, the first session is something that is going to be focused on the online advertising. So there are a lot of applications where one can think of applying the reinforcement learning models. And so business is one place where we can, yes, use these methods and uh, use them to a good advantage. We could also think of using them for trading stocks and shares, um, wherein the method is going to now learn from the uh, all the strategies that are required for buying a stock, selling a stock, or even holding a stock. So a proper RL model that's developed for a trading system would possibly be recommending you on what kind of strategy that you are going to adopt. Fine. And then, of course, you have the pick and place activity, which is a typical activity for a robot. And now you have RL techniques are also, able to come up with what is called as core robot controls, meaning robots can now work as a team and then, start solving a problem. So it's something like, for example, playing a football, wherein you require different players to coordinate together to win the game by putting the goals, is something similar to that. You can think of RL now being applied for all these robots who are going to work as a team. Okay, so I have one question here. If historical data is not used in oral, then what type of data does it use? Okay, that's a very interesting question. Yeah, so maybe at the end of this exercise, I think you will have some bit of idea on what kind of data that is actually getting generated, right? So we'll reserve this question to the end of the session. Possibly one of you can try to answer this uh, after we complete the session one. Right. So if you look at the entire crux of the reinforcement learning, it all is connected with the diagram that you see here, which is the most important one. I would say this particular slide is the most important takeaway slide for you. from the today's exercise, especially from the RL session. Please note this down, or you can refer to this later. But this is the essence of the algorithm, right? So there is an agent which keeps interacting with what is called as the environment, right? And then when this agent is trying to, so what this agent is trying to do, the agent is possibly trying to learn a task. For instance, in the pick and place example, the robot will be shown possibly a coffee cup or a teacup or a ball, and then it's supposed to go walk towards it and pick the ball, right? And so the agent now, it's not a physical agent. When I say agent, you don't have to think about the agent as somebody, as a person, right? So it's not about a person, it's not about being a person. It's just a way of quantifying things. So what does the agent do? The agent interacts with the environment, or from a code point of view, you can safely assume that the agent is a separate piece of code which interacts with environment, right? And so when it interacts with the environment, uh, it gets a reward based on how it performed. If it performed well, then it's supposed to get a good reward for it. If it is not performing well, then it's not going to get a good reward, possibly a bad reward, but then it will definitely get a reward for whatever it does. So the agent always interacts with the environment. And then this environment, what does it do? It's something that is outside of agent, whose only role is to, give a feedback, the so-called evaluative feedback to the agent in terms of the reward signals. So that is the primary purpose of the environment. And then you have also what is called as the state, which is going to be part of the environment, but independent of the agent's control. So agent cannot control a reward, agent cannot control a state. The agent can only control what? The action that it is going to take. So you see, it's very constrained or confined to this particular exercise of selecting an action. The agent is going to select an action, and based on which the environment is now going to give a feedback in terms of the reward. So then what happens to the state? State is something that is uh, outside of control of the agent. And so once an action is taken, we presume that the state has changed, right? So once an action taken by the agent, then you will get to see a state change that happens. So it can never be uh, possibly in the same state, except for when the agent successfully completes a task. That's when we assume that the agent has reached what is called as the permanent state or the terminal state. So we'll come to that little later, but then this is the crux of the model. So you have an agent who's trying to learn. Their only purpose is to learn from the task, right? And it's supposed to take an action. And this is now fed to the environment, and the environment gives a feedback to the agent in terms of the reward, right? And so how is the agent able to learn? It is only by means of what is called as the reward structure. So if you ask me, the second best or the second most important element of the reinforcement learning models lie in the rewards that the agent is able to get in the learning exercise. So these rewards are typically under our control. Whoever designs the RL model or the RL algorithm, they are going to now control the reward structure that's used in learning model. So the state, like I said, is independent of the agent, and outside of the control of the agent. The agent's only thing or only task is to uh, take an action and then get a reward. Take an action, get a reward. This iteration keeps continuing until a terminal stage. So that is the fundamental idea behind how the agent is going to interact with the environment and how possibly the RL learning exercise can end, right? So when it starts, it takes a kind of a random action. So to start with, if you see, that's another common behavior of a reinforcement learning model. When the agent starts to learn, it starts with no experience, right? It starts with no experience. So when the game starts or when the exercise starts, there's no experience for the agent. But as the time progresses, as the agent is able to take more actions, it takes an action, then it gets a reward for it. And then according to that, it again takes an action, then it gets a different reward. So if you go through this entire iteration, it would have gathered enough amount of experience, which it can use for the learning purpose. So this is what we mean by the historical data in the RL technique. The sequence of the actions, the sequence of the rewards that the agent is able to get is nothing but the experience of the agent. All right, so that's about the interface, agent environment interface. Yeah, so here is a formal definition of all the terms. We already saw what is an agent, right? So agent is someone who's able to learn to perform a task, and its objective, if you look at, is acting kind of greedily. I mean, it's trying to maximize the total rewards that it is able to generate by performing the exercise. The environment is the broad um, surrounding in which the agent is able to do these activities and is able to get a reward for it. Yeah, this is another important thing to understand, the so-called policy. In reinforcement learning, we keep seeing something on the policy side. So what is a policy? Policy is it's a mapping from a state to the actions, right? So when you are in a particular state, what are the kind of action that you need to take is called as a policy. For instance, all of us drive home from the college or from the office, right? And we know what is the route that we are going to take when we go for the destination. So in a way, if you think of that destination, which is your home, as the terminal state or the end state, we know at a given traffic junction, we got to take a right or a left, and that's how we reach the end destination. So while performing this activity of starting from point B and trying to reach your home, you would go through a lot of traffic junctions wherein you have to decide on whether you want to take a left, whether you want to take a right, or whether you want to head straight. So I could simply say the policy is, if you are at a traffic junction, right? The policy says that if you want to reach your home, take a right. And in the next junction, you take a left. That's a policy, right? So irrespective of so many other ways in which things can be performed, this policy is a clear rule which can guide the agent or even us in terms of what is the optimal activity or action that needs to be taken from a given state, right? So what is the state here? Being at a particular traffic junction, a specific traffic junction in a city. So you can think of it that way. So when I say at a traffic junction, it's a specific traffic junction on way to your home. And then yes, we have the reward structure, which itself is a very important component, because the success of your RL method lies in how well you design the rewards. You see, when we look at our kids, I could relate this to the kids at home. When typically you want to perform, you want them to perform a task, and you ask them to do it. They may be reluctant to do, or say, Papa, why should I do it? Okay, I will not do this. Then you attract by saying, okay, I'm going to give you a 5-star chocolate. And if you are able to complete this activity successfully, I will give you this chocolate for you. And so the attraction for the kid or the child now is the reward that it is able to get in terms of the 5-star chocolate. And so it's now able to perform the task. And so you also say that if you don't perform this task correctly, I will beat you. Okay, so that's a kind of a negative reward, right? And the positive reward is getting the chocolate. So what will the child do? First, it could be doing things wrongly, and so it could be getting beating from us. But then once it's able to learn what is the actual way in which a task is to be completed, then it will be able to successfully complete it. And so then it will end up getting a chocolate. So our agent can also be thought of in a similar way, where it's your ability to bring in an appropriate reward. It could be a 5-star chocolate, or it could be a car, it could be anything that is able to make this agent learn successfully. And that's the whole idea behind the reinforcement learning. So for simple problems that we are going to see today, the reward structure is fairly straightforward and very easy to relate to. But then if you look at a very complex learning problem, the ones like the chess, the ones like the go, how are you going to reward the agent in terms of their performance, right? So that's going to be a huge challenge. In fact, today we have all the researchers across the globe who are trying to do, research on how to structure these rewards. So developing a reward structure itself is a PhD exercise. It's not a very, very easy thing to do. But then for a simpler application, we don't have to look at the reward structure and doesn't matter much, right? A simple discrimination in terms of rewards will actually serve the purpose. Yeah, so any questions, quick questions? Okay, so now let's look at the um, different models or different types of RL algorithms that we can see. I mean, we kind of classify them into different sets or different categories based on what is called as primarily a policy that's used inside the RL technique, or it could be based on the type of solutions that you're able to get, or it could be based on the models of the learning task. When I say models, the model is literally here to mean the probability distribution that is underlying a learning activity. So we can typically, assign a transition probability distribution for the underlying learning task, and we can use that as an exercise for learning purpose. So the methods which tend to use the transition probabilities, for example, MDPs, the Markov decision process, these are all processes which rely on the transition probability distribution, right? So if you do not use them for the learning purpose, then they are called as model-free, uh, exercises or model-free algorithms. And there are methods which can allow you to get exact solutions for a given set of learning exercise, or it could be perhaps an approximate method, which may not be the ideal one, but then it's going to allow us to learn the task that is at hand, and it's able to solve the problem for us. So based on the solution that we are going to get out of the RL technique, we can classify them into exact methods and also approximate methods. Now, in terms of the policies, it can be classified into both on policy and off policy methods. Uh, I know it's a little difficult at this point of time. Just keep it with me and try to understand that this is when an on policy is when the action that is taken by the agent is the same as the policy that is being developed. So if I have to relate this to our previous example, I talked about the traffic junction, right? So I said, if you reach a particular traffic junction, you need to take a right if you have to head home. But then if I don't follow that rule, what happens? So then my action is different from the policy. So if the policy for you is to start from point B and go through these different traffic junctions and reach your home, if you don't follow that policy, there could be possibly an alternate route that exists, which also leads you to home. So although the policy says at a specific traffic junction, you take a right and the next one you take a left, you sort of violate this policy saying, okay, I'm not going to go right. Instead, I will go left. So then at the traffic junction, now I take a left. And at the next junction, possibly I take a right. I possibly go to the same area or the same road. So this is the underlying idea of on policy and off policy. So if has to be an on policy kind of a thing, the agent will take decisions which are governed by the policy, right? The policy of what action to be taken at a given state. And if the agent takes a different kind of an action, then we call that as a off policy evaluation or off policy method. So when the action is the same as the policy that is being evaluated, then that's called as an on policy evaluation. And the action that is taken by the agent is different from the policy that's being evaluated, then it is called as the off policy method. So now we will get into, looks like some questions. Okay, right. So if you look at the exact solution techniques, I've not kept the approximate methods here. So if you have to really look at and study this reinforcement learning, in depth, you have to refer to a book written by Richard Sutton. That's a go-to text titled Introduction to Reinforcement Learning. And they've given it in a very nice way. It's a book that is quite technical in nature, but at the same time, that is the only textbook that is going to give you a fundamental idea. I mean, that is like the Bible of RL. So someone has to look at and see this in depth. You're always welcome to refer to that particular text. In fact, I also learned from that particular text only. So my reference is from Richard Sutton. So the tabular learning that is given here is basically a set of methods that are falling into a category of exact solution techniques. So when you look at the exact solution techniques, it is also depending upon the type of problem, but then these are the techniques that are being used. So the first one that you see is basically the multi-armed bandit problem, but essentially this is mean to say a greedy algorithm, right? It's actually a class of problem, but it is listed here as kind of a method. But then this is equivalent to saying I'm using a Epsilon greedy algorithm. So it's a greedy algorithm that is being exploited inside the first topic, that is your multi-armed bandit. And in fact, that is the exercise for today, because that's the most basic of the RL. In fact, there is no learning that is taking place here, but then this is a fundamental idea behind the sophisticated RL techniques. And so then we have the Markov decision process, which relies extensively on both the Markov decision process and the dynamic programming. They rely on the transition probability distribution. So we want to solve the task using these two techniques, the MDP and the dynamic programming. You require data sets where you also have what is called as the stationary transition probability distribution, so without which you cannot get an answer. So they rely on the transition probability distribution a lot. So then comes your Monte Carlo and the temporal difference methods. These are all a little advanced methods. Okay, and then these are also very useful in terms of getting an exact solution. Okay, so these are based on some sort of a sampling technique which is being used, which is why they are categorized in a different class altogether. So Monte Carlo methods, temporal difference methods, these are going to rely on a little advanced concepts of tabular learning, right? And so, as I said, there are different methods that are given inside the exact techniques, and it's going to take a lot of time to learn what each method is. So the idea for today is get you oriented towards what is RL, right? So we will stick on with some basic examples, starting with your multi-armed bandit. So what is this multi-armed bandit problem? So it's a problem that is quite basic in nature, and it's very, very rudimentary one in terms of the reinforcement learning models. So the problem essentially is, you are faced with a choice among k options. If you look at the right-hand side image, uh, that's an image which is specifically given here to relate to the bandit that I was talking about. And you could relate this to the casinos, right? Where will you see these machines? These machines are found in the casinos. And so people typically gamble in the casinos. And so you kind of pull a lever in the machine. And so depending upon how the numbers are going to turn out, you will get a jackpot. So that is called as a bandit, right? And then you have, different machines that are lying inside. And so you can now start to choose between different bandits or different options. And then you pull a lever, and then accordingly you will get a result. Okay. So some of these bandits may be favorable for you. Some may not be favorable for you. And then your objective is to now choose between these bandits successfully. So given a choice between all these machines, which lever should you pull? Then your exercise is to identify that most probable or most likely kind of a lever, which when I pull will get me the ideal reward or a maximum reward. So you see now casinos are directly connected with the rewards, and then people tend to play a lot in the casinos, in the bandit machines, and then they pull these levers, and then many of a time they don't end up getting a reward, but then some point of time they do get the reward, and when they get it, it's going to be huge. Okay, so now we are going to model that problem as an RL exercise, right? So how can you think of this multi-armed bandit as a oral model? Okay, so that's what we are going to look at. And then uh, when you select a particular lever, when you pull a certain lever, you are also going to get a reward from an underlying distribution. Okay, so how does the reward come in? Reward comes in from the distribution that is going to characterize a particular machine or a particular bandit. And so every time you pull a lever, you sort of look at, okay, which lever you have pulled, and then accordingly you refer to a table and get the reward from the distribution. So it's like going back and looking at your distribution table. Okay, I pulled this lever number 1, so I go and refer to this distribution, which is going to give me a particular reward for it. And so what is the objective here? Objective is I want to maximize the total reward that I get from this entire exercise. So if I pull this lever 100 times, then ideally if I assume a reward of 1 for every right pull, then possibly I'm trying to maximize my total reward. So 100 times I pull a lever, I get a value of 100. Okay, but it's not the case that you will get 100 at the end of the exercise. The idea is when I pull a lever, I may get a reward of 1, but then I could also be getting a reward of 0, right? So that's how it works. The machine does not give you a reward every time. So there are many times when you have to pull a lever, but then you do not get any reward. Okay, so that is the underlying idea. So there are many iterations here where the agent, which is our RL agent, is trying to choose between different choices or trying to choose between different options. And these are quantified by what is called as the K. So if you refer to the textbook on what is this K, you can typically see that they term it as K-armed bandit, where the value of the K can range from 1 to n. So let's say if I take a K of 5, then it's equivalent to saying that I'm going to have 5 bandits and I'm going to pull these 5 levers, right? So that is the K which we are going to see in the multi-armed bandit. So the term multi is related to the term K here, and the K is nothing but a value that's going to range from 1 to n. Okay, and what is the objective? Objective is to maximize your total reward at the end of all the iterations, right? So I think I've given enough context to this problem. And so we will now see an application of it. Yeah, so before we move into the application, let us also look at what is the idea behind the multi-armed bandit algorithm, which is the Epsilon Greedy. Basically, you're trying to maintain a list of action value estimates, all right, over a period of time. So you pull a lever, you estimate the value of the action, and you keep that in a list. Okay, and then once you store it inside, then you sort of when the next iteration comes in, you sort of use a policy like a greedy policy to select a particular action. So how will I select? I will look at this list which I've already kept in place. Then if I adopt a greedy policy, then I will pick out a action from this list which is going to maximize my reward, right? And that's the greedy policy. So why the term greedy here? Greedy because I'm always trying to maximize my reward, right? So given an option, the agent always tries to maximize the reward, and that is why it's called as a greedy policy. So I adopt a greedy rule and then I select an action from the list which is possibly going to give me a maximum reward. Now you can think of this way: as and when the iterations proceed, when the agent starts the learning, in fact, there is no learning here. I'm just saying for the sake of completion. So the agent, when it starts to learn, it starts with no experience. And when the experience progresses and the iterations progresses, you will see the estimate of the action is going to change. So the value of this action that you are going to take will keep changing, right? It's not going to remain the same. So because these action values keep changing over a period of time, and you are adopting a policy of being greedy, that's how you are able to learn, right? And the thing about here is this particular algorithm, it's a very unique algorithm, and it's also something that is underlying for all the RL agents, irrespective of which problem you look at it. there is a fundamental idea behind application of all these methods. The first one is exploitation, and the second one is the exploration. So if you ask me what are the important ideas from here is explore or exploration versus exploitation. So what is exploration and what is exploitation? So that we have to see, right? And I said here, for most of the part, you will do what is called as the exploitation. So this is the most important activity for any oral algorithm, right? Whereas this one is, okay, if I put this as the most important, this is like, second important thing to do. So what is exploitation? Exploitation is, I have a list of action value estimates. When I want to take an action in the next iteration, I have to look at this list and take the maximum action, or I select an action which is going to give me the maximum reward, right? And that's the exploitation. So what do? I am exploiting this list of the action value estimates that I already have, right? So that is about the exploitation. Then what is exploration? It is where you start the agent is venturing out, it's taking adventure, right? It's going to take an action that is not prescribed, right? It's going to take an action that is not prescribed. So the agent tries to take a different sort of an action that may not really result in a positive reward or even a good reward or even no reward at all, right? So the agent's ability to take an action is take an action that is not in the list of actions that are already there and which is going to give you a good reward. That is what we call as the exploratory part. So it's like taking a random action, right? So to put it simply, it's taking a random action from the available set of actions. So it's something like saying at a traffic junction, instead of taking a left and right, or you face with a choice of taking a left and a right, and so you sort of toss a coin and then choose which way to go. So head comes, you go to the right, tail comes, you take a left. So exploration is something similar to it. So the agent also adopts a similar exercise. It's going to always do what is called as the exploration for some of the iterations. Now, what happens if I remove this entirely? Any idea? Let's assume if I do not do this exploratory part, I only keep doing the exploitation part. Can you tell me what will happen? Or you can type it in the chat box. Okay, someone wants, yeah, exploitation again, right? Understood. So exploitation is, I'll give you a simple example. Let's say there is a policy and this policy states that if you are in state 1, you take a left. If you are in state 2, you take a right. If you are in state 3, take a left again or go straight. Fine. So this is our list of action values. And for possibly all these actions that are suggested, it's a suggested list, right? You are in state 1. What is this 1, 2, 3? 1, 2, 3 is the state of being in a particular junction. So let's say the traffic junction 1 is your state 1, traffic junction 2 is your state 2, and traffic junction 3 is your state 3. And so the policy suggests that if you are in state 1, you take a left. And if you are in state 2, you take a right. If you are in state 3, you take a straight. This is a policy. Why would we do this? Because that's when we get a maximum reward, right? So when you adopt this policy, perhaps you would possibly get a higher reward at the end of this exercise. That is, after I cross through state 1, 2, and 3, I will end up getting a higher reward for that. But then if I do a different action, so I go by the book. So you can think of this way, exploitation is when I go by the book. I don't deviate from the rules. If I deviate from the rule, then I call that as a exploration. So the same thing when the agent is trying to perform the action. So instead of selecting a left in the state 1, let's say if it selects a right. So the prescribed action for being in state 1 is left, but then the agent is taking a action that is not prescribed by the rule. So now it's going to take a right. So this is what we call as the exploration. So when I go by the book, when I go by the policy, it's the exploitation where it's supposed to give you a higher reward, but then exploration comes in when you deviate from the rules. So what's the takeaway from here? The takeaway from here is you have to deviate from the rules if you have to learn. So if we don't deviate from the rules, we can't learn everything. So someone wants to learn everything, then you sort of explore, you sort of venture into different things. This can also be related to our actual real life, where we see people who are successful in life, who have experimented most, you have traveled most, you are culturally diverse. So typically these are the people who are going to have a very good perspective of the life, right? So we kind of look at them as, our role models. So someone who has gone there and done everything. So those are the people who have sort of explored and sort of learned. And so the same thing applies here. The agent is going to possibly perform better if you allow it to explore. So for some iterations, you have to allow the agent to explore. So for some iterations, you allow the agent to do the exploratory part. And for some iterations, or majority of the iterations for that matter, you want the agent to exploit the action. So that's the general idea of the bandit. But then if you look at it, this same idea keeps repeating in all the methods that are seen in the reinforcement learning, right? So although it's a very simple exercise to do, this is the same thing that also comes across in all the different oral methods that you will see. So now comes the, the code. So the problem that we will see, I will explain a little later, but then this is how you can perform the action in a computer, right? This is how you can program a computer to do this selection of a action. So this is a pseudocode for the multi-armed bandit example, wherein we adopt what is called as a random selection. So what does it do here? This agent is going to act wild. It's not going to behave in the way that you want. So it will always do an exploration. Simply put, your exercise is now to develop an agent which only does a pure exploration and no exploitation whatsoever, right? So I could say pure exploitation, exploration and no exploitation whatsoever. So how can I do it? So let's assume we are trying to code this in the Python or whatever software, whatever it could be C or C++. Anything is fine as long as when you can implement the code. So for the action list that are allowed from 1 to K, Remember, K is the number of bandits or number of levers or number of bandits. The idea is to learn over a period of time, and that is given by the iterations. So it's something like allowing the agent to learn in, let's say, 10,000 iterations, something like this. So I am going to allow an agent to run for n iterations, for example 10,000 iterations, and allow the agent to take a random action. So each iteration, I keep selecting a random action from the available set of actions. So I keep doing this, and according to the action that I take, I have the reward list. You see now this is your not under the agent's control, right? Reward is something that is given by the environment. So according to the action that is taken by the agent, you will get a reward from the master reward list. You will get a reward from the master reward list. This is a simple lookup table, right? It's like a Excel lookup table wherein I refer to the data and then I select a reward. So the reason for looking at the data is to get the reward, not to use them for training, right? Please keep this in mind. In reinforcement learning, the only thing that allows the agent to learn is by the reward itself and nothing else. So the reward is the only means by which we can communicate to the agent and allow it to learn. So the reward comes from the master reward list, which is basically a lookup table. Okay. And from there, we refer the value and give it as a signal for the agent. And then the agent is now going to accumulate the total rewards. So it keeps accumulating whatever rewards that it gets. So it gets a reward of +1, it accumulates, it gets a reward of 0, it accumulates, gets a reward of -1 also, it's going to get accumulated, right? And so over this 10,000 iterations, you now sort of trying to see what is the maximum reward that you can come up with, right? So this is the random selection algorithm where there is no involvement of any greedy policy or anything like that. This is the bare simple exercise that one can do, and we can compare that with your actual algorithm that is used for MAB, that is your Epsilon Greedy. So what is this Epsilon? What is this greedy? I talked about greedy some time back. Greedy is, yes, it's literally meaning greedy. You're trying to be greedy because you want to maximize your total rewards, right? And then you have what is called as epsilon, which is actually a Greek parameter. Many of you would possibly know this, right? We have this Greek parameter epsilon. So it's the term that is denoted for using or referring to what is called as the epsilon. And the epsilon is directly connected with exploration. So if you see in the algorithm somewhere, I will mention epsilon here. So you see here, I mentioned the probability epsilon. So it's a probability value. It's a probability value with which you are going to explore your action. So probability of exploration, probability of exploration. So what do we mean by probability then? So I have, let's say, 10,000 iterations, right? 10,000 iterations. And if my epsilon is 0.1 or 10%, what it simply means is for 10% of the iterations, I am going to rely on exploration. And that's not it, right? So you are also going to do the exploitation part, but then you are saying that allow the agent to explore for 10% of the iterations. So 10% of 10,000 is 1,000, right? So out of this total 10,000 iterations, 9,000 iterations, the agent is going to do an exploitation. And for the rest 1,000 iterations, it's going to do a exploration. Okay. And so how does it exploit? The exploitation comes from this particular term that is written here called as argmax. Argmax is nothing but, if I have to relate to the previous slide, I talked about a list of action value estimates, right? So that algorithm is in fact now referring to this list of action value estimates. So when I say argmax of QA, essentially what I mean is you basically refer to the action list and pick an action that maximizes your reward. That's it and nothing else. So for 9,000 iterations, you sort of refer to this action list and keep picking an action that is going to maximize the reward. But the beauty here is this value, right? The so-called maximizing the total reward also keeps changing from iteration to iteration, right? Remember, when the agent starts learning, there is no experience. So the experience is now sort of stored in this list, the action list, where according to the experience, different actions will get different rewards. And so when the agent is now trying to do an exploitation, it will go back to the master list and it will try to pick up a value that is going to maximize its total reward. So it's like selecting in the case of a program, it's like selecting a particular index or the key which will result in the maximum reward. Okay, so that is what we mean by the exploitation. And so you either do a exploitation or an exploration in a given iteration, and then you accordingly get a reward, right? You accordingly get a reward. And then so you increment, how many times. These are all, for the purpose of something else. These are not really value adding steps. But then these are possibly used for computing, for instance, what would be the average cumulative reward that the agent is going to get at the end of an exercise, or it could be something that is useful for plotting a graph. So some of these lines could possibly not add any value to the algorithm except for some derived analytics. So when it comes to the real crux of this method, this is where it's able to now gather the experience. I talked about experience earlier. Where does the experience come in? Here is where the experience kicks in. So the experience of the agent is now stored as the Q of A or this action list. Remember I talked about action list. What is the action list? That list is going to store this values of Q of A. Okay. And so you see now when I go to the next iteration, I try to take an action that is going to maximize my total reward, right? So I keep updating my Q value or the value for the action that I take in the action list, and I keep updating it. So there are 9,000 iterations in which the exploration is being done, or the 1,000 iterations in which the 9,000 iterations in which the exploitation is done, and 1,000 iterations in which the exploration is done. I kind of apply this update formula to keep updating my action list values. Okay, so that sort of gives you the overall idea behind how the greedy algorithm is going to work, right? So this is the Epsilon Greedy algorithm, right? I'm sure you must have got fair bit of idea, the basic steps that are involved in implementing the Epsilon Greedy model. So we'll take up an example here. It's an online advertising example. It's a quite popular one. So I've also taken up an image for which, and I put it here. So let's say the exercise here is I want to show certain ads in the web page. Okay. And so typically all these online advertising agencies, what they do is they come up with different advertisements that are going to be posted online. So for instance, this is a type A kind of a content that is in the website, wherein you put in your offer. You will say, okay, click here to get the maximum offer, maximum discount. And then this is the other way of putting an ad. So you see what is different between the two. This is A way of putting it, and this is B way of putting it. The difference between the two is in the way which the ad is being presented or the page is being presented to the customer, right? And so the B is quite different. It sort of has a different design to it. It has a different text attached to it. Possibly the headlines that go along with it could also be different. And so you are now trying to see which sort of ad is going to work well for you. Okay, so given here is a very crude example of just two advertisements, but you can actually work with, let's say, for instance, 10 different ways of posting an ad in, let's say, a Facebook or even any other social media, which will allow you to gather clicks. So when an appropriate ad is shown to a person, the person is going to click on that ad, and thereby you are able to generate revenue out of it. Okay, so we will take up this advertising example. So the ads, when you look at primarily, before you run this experiment, you never know uh, how these ads are going to behave. But for the sake of our application, I've taken up a data where the rewards are already there, meaning we already have certain experience of clicking through this ads. So I'm sort of now giving you that data to you. Okay, and the data is only purely on the reward front and nothing else. Like I said earlier, we do not use any other data for the learning purpose. We primarily use only the experience data, and what we have here is also the experience data. And so for this example, we will look at 10 different ads. And so the idea is to pick out the optimal ad which could possibly result in maximum revenue for us. So given a set of ads, which one to be selected for posting in the website is what we need to look at. And so the goal is to find what is called as the effective ad. So there could be one or two ads which could be effective, and that will gather more revenue for you. And so how do we find them? So in marketing parlance, this is actually called as A/B testing. In fact, in the digital marketing parlance, so this is actually a topic that is touching upon digital marketing. So the digital marketing runs all this A/B testing of ads. These are all real life applications. And so the data is also something quite similar to it. Okay. So this is the example that we will use. And in fact, you are going to use it, right? And yeah, this is how the data is going to be looking at. Right. So you have a list of ads starting from ad 1, 2, 3, etc. until 10. Okay. The Excel file will actually be consisting of 10,000 rows. Okay, 10,000 rows of data, wherein you will just find these numbers of 1 and 0. So what is a 1? You are showing the ad. So first time when the customer is looking at it, he is able to click through the ad. So when the customer clicks on it, you get a 1. but in the subsequent, subsequent refresh of the pages to different customers, you are not seeing anybody clicking on the ad which was shown to them, right? And there is someone who's going to again click on it. So like this, you have for each ad, 10,000 rows where you will see numbers of 1 and 0, which basically denote rewards, right? So when a customer clicks on the ad, when you have a click is equivalent to getting a reward of +1. No click is amount to getting a reward of 0. So that's what it is in the Excel file. This is all you have in terms of the data. Now you are going to use this for learning purpose, right? So the Epsilon Greedy algorithm, or the code that I showed you earlier, is what you need to implement and try this out. Okay, and I will give you the URL for this. So I'm putting the URL in the chat box. Okay, so please click on this link to download this file. So you should be able to download the CSV file. I hope you are able to see the screen, the Excel file. Okay, so if you look at this file here, I'll just quickly show you the kind of rewards that you're going to get from posting all these ads. Right, so what do you see here? You will see for certain ads, you get a very low reward. For instance, this is ad number 6. This is ad number 6. So before we even start applying our technique for getting an answer to this, which ad to be picked, we know from here that the maximum one is in the last ad, which is ad number 10, right? That is where you are able to get a maximum reward. So if I look at the maximum one here, the maximum one is going to be the ad 10, which is going to give me a reward of 2,695. Now, what is the next best ad? Next best one looks like the ad number 8, which is now allowing us to get a reward of again over 2,000. So if we look at this particular data, the two ads which stand out are the ad number 10 and the ad number 8, and both are allowing us to get a reward more than 2,000. And so our agent, when it is able to learn from, if at all it is able to learn, it has to pick this ad number 8 or ad number 10, right? So we want ideally these two ads to be picked often by the agent. So when the learning starts, when the method starts to work, you will see that it will start picking up. In the first example, you will implement the random selection, because that's the bare minimum implementation, which does not involve any uh, idea of queue updates, and you will also easily understand it. So that will now select all these ads randomly. Now, can you tell me what will be the kind of rewards that you will be able to get by selecting randomly? What do you expect will be the reward that is going to come from uh, this particular application? Can you tell me a number? Yeah, I want you to try it out. Question is, what do you think will be the rewards? It need not be exact. It cannot be exact. All that I'm asking is, what is the number that you are expecting out as the result of application of random selection? Okay, we have a number here, 1112, 2695. Rajashekhar is saying 2695. Okay, 2695 is possibly for the most efficient agent. You cannot get 2695. I don't think you can. Okay, it will be a random number. Okay, it's going to be random, agreed. But all that I'm asking is the ballpark figure 1703. Dr. Budesh Kanwar says 1703. May I know what is the rationale? Okay, that's ad number 1 again. You are trying to pick from the ad. See, if you are going to explore, you are going to pick the ads randomly, right? So you sort of expect the rewards to be an average. So I would possibly expect my agent to get a reward somewhere close to 1200. You get the idea? You have 10 different ads. No, it's not 1106. Okay, I am expecting the random agent to get a value that is closer to 1200, possibly upwards of 100 or downwards of 100, somewhere close to it. Okay, 1295. No. See, the agent is not going to take only one action, right? It's going to take multiple actions in each iteration. So the code that you are going to implement will start from here. So these are like iterations. Okay, I will type it down here. These are like iterations here. So this is iteration 1. Iteration 1, iteration 2. So like this, I have until iteration 10,000. So for this application, you can't go beyond 10,000 because this is a maximum amount of iterations that you have. Okay, and so if you are in iteration 1 and if you pick out ad number 1, then you get a reward of 1. If you are in iteration 2, you will look up the second row, not the first row. Okay, you get the idea? And that's how you have this 10,000 rows. So it's like, different ways of throwing the ads. So you're not going to get the same reward every time you choose a particular ad. So for instance, if I pick out ad number 9 in the iteration 1, the agent is picking out this ad. He's going to get a reward of 1. But then in the next iteration, he will get a reward of 1 again. But in the third one, if he is picking the ad number 9 again, he will get a reward of 0. So that's how it goes. We get the general idea. So 10,000 iterations. You've also seen which sort of ads that the agent needs to select if it has to behave optimally. And so we ideally want the agent to select ad number 10 or at the best ad number 8. So I want either this ad number 8 to be selected by the agent, or I want the ad number 10 to be selected by the agent. So let's see if it's able to do this. If you implement the code. Yeah, so this is the code for you to implement. This is the code for you to implement the random selection. Okay, so I'll keep this visible to you so that you can use this pseudocode and try this out. So I think we have about 20 minutes. So use this idea to implement a code in your Python or whatever software that you have. So you do not require any libraries apart from the default ones. So for example, the only library or a couple of libraries that could be useful here is your NumPy and Pandas. And this will be typically, installed in all the software, or you would have already installed it for applying your machine learning models. So if you have NumPy and Pandas, I think this should do. Other than these two, you don't require any other library for the session. So how do you start? You sort of before starting the loop, you initiate a list, an action list. You initiate the count to 0, and then you run a for loop kind of a thing from 1 to 10,000. And in each loop, you select a random action, and then you refer to the table. Okay, so you refer to that Excel table, which I showed you. And then how do you refer to the table? You will refer to the table by means of, row, comma, column. So when you read the file the first time, the ads optimization.csv, read that and store it in what is called as a reward list. So reward list will store data from ads.csv, right? It will store the data from the ads.csv file. And so every time you take an action, you refer to this reward list to refer to the corresponding reward. So if you are in iteration 2, let's say you're in iteration 1, your row is 1 according to the ad that you selected, and there are 10 columns here. So your column values will range from 1 to 10. So let's say you're selecting ad number 1, then the column value is 1 again. So for the first iteration, you refer to the 1, 1, and so that will give you the reward value from the list. In the second iteration, this will now change it to 2, but possibly this time you could have selected, let's say, ad number 3. And so in iteration 2, you refer to row 2 and column 3 to get the reward. So like this, the row value will keep changing from 1 to 10,000, and the column values will keep changing from 1 to 10. Okay, code is not visible, I'm sorry. Yeah. Sorry about that. Okay. So yeah, I was writing on the NumPy and the Pandas library, and then yeah, so the reward is referred from the reward list. You see here, I have a reward list that is coming from the ads.csv file. Okay, so you have the reward list, which is coming from the ads.csv file. And then each loop, you take a random action, which means you are just picking a number from 1 to 10. What is a random action here? Random action is picking an ad from 1 to 10, right? So you sort of pick a random action and then you refer to the Excel file, which is now getting stored as the a reward list table inside your Python software or any other software. You refer to this list based on the row and the column. Like I said, iterations don't go beyond 10,000 iterations. The maximum value is 10,000. And for each iteration, you have a choice to choose from 1 to 10. So if I do that, what will be my reward structure? So every time you take the random action, you refer to the reward and keep a total count of the reward that you get from taking that action. So 10,000 iterations, 10,000 rewards, which are coming from your Excel file, each of which going to be either 0 or 1. Okay, I hope the screen is visible now. Are you able to see my screen, which consists of the pseudocode?
Yes, sir.
Yeah, so just try this out. I will show you the code in another 5 minutes. So I'm just trying to give you some time to experiment. So if you're done with that exercise, the next one will be to move on to the uh, greedy exercise. So the same code that you can use for the random selection now can be modified for Epsilon Greedy. Okay, so just a few few tweaks here and there, and you should be able to get the code for Epsilon Greedy. So as you can see, most of it are the same except for uh, the action selection part, wherein now we are going to use this argmax component for selecting the action or the random action. Okay, so you'll have a piece of code which accounts for this. And then you will also have a piece of code wherein now you use an additional formula to update your uh, action value, right? So this QR of A that you see on the top is now going to be revised in each and every iteration using this formula that you see here. Okay, so this reward value is the value that you are getting in each iteration by looking up to the list. So you refer to the list, get the reward, and use that inside the update loop to get an updated action value. And then you also keep a count on your total reward that you get from this exercise. So that's going to give you a total value in terms of the rewards out of all the 10,000 iterations. Okay. So now I think I will show you the code. See, a general guideline in terms of implementation is um, don't start with the code. Idea is to start doing it on your own, trying it out on your own. You will end up doing a lot of mistakes, but then eventually you learn. So try to do this particular exercise on your own. Try to develop the code on your own. But if you are not able to do it, and that is when you look at the code to see where you gone wrong. So are you able to see my screen? Okay, so this is the IDE. Okay, and as you can see, I have just imported some basic libraries here. So the first exercise is random selection with no learning, right? Random selection with no learning. So yeah, we also import the random library because I want to use the random function. And so this is our Q of A, right? This is our Q of A. So to say from the slide in the slide. So this is the sorry, this is not the QFA. This is the ads that are getting selected. So what is the ad that you are selecting in each and every iteration? So this is again not going to add any value, but this is required for instance, we want to know uh, what was the ad that I selected in each and every iteration. Then I would keep a list of ads selected in each iteration. Then you have the rewards got. This is your reward list, which stores each and every iteration reward that you get. So iteration 1, you get a reward of 1. You store that here. Iteration 2, you get a reward of 0. That also gets stored here. And this is where your actual loop starts. You can relate this to the slide. So for n in the range of 0 to n, so I start from 0 and move on to the max value, which is your 10,000 iterations. Okay. And so for each iteration now, I'm going to select a random ad. So you see, now I'm selecting a random ad uh, using the random library and rand range function. I'm selecting a random ad, and then I append that to the ads that I select in each of the iterations. So store the random ad selected in the list. Then I do the lookup table, which is the same as the one that I showed here in the slide. Okay. And so now I refer to the reward. And okay, there is a reason why I'm putting it value greater than 9,500. You can simply append this. You don't even have to have this. So possibly when you write the code, you can write it down this way. This will do. So irrespective of whether your iteration is more than a certain number, you keep appending your rewards that you get. Okay, right. And then you append your total reward. So total reward, if you look at this, initially we set this to 0. but then as and when you progress through the iteration, you accumulate the total rewards. And then I print the total reward that I get at the end of the iteration. Okay, so let me run this one and show you before I show the other one. So let me run this code. And this is what you get. Okay, let's go to the graph later, but let us look at. Remember what was the reward that I was showing you? The expected reward? What was the average reward that we came up with? I calculated an average reward, right? And I showed you that it is going to be closer to, so that was somewhere around 1268 or something. Look at this answer, 1253. So I said the value that you are going to get out of running the random selection will be somewhere close to 1260. So here you have the random selection algorithm is giving you a value of 1253. Okay, and so what is this table that you see? This table is the ads that it is getting selected in each of the iteration. Okay, the last 1000 iterations. So this particular table, the small table that you see here, is a result of the last 1000 iterations, that is after 9000 iterations. Which are the ads that were selected maximum? Okay, so the total iterations for look for the count is about 1000 here. So out of the last 1000 iterations, the random agent was selecting the ad number, not the ad number. Please keep in mind, this is starting with 0. Okay, so 0 to 9 is the value for the agent. So what is the value for agent? The value for the agent is, I give a D, right? D is 10. So the agent is now selecting. So 0 is equivalent to selecting add 1. 1 is equivalent to selecting add 2, and so on. So the last number will be 9. Okay, 9, which refers to or equivalent to selecting add 10. Okay, so if we go by that logic, what is the 8? 8 is equivalent to selecting add number 9, right? So the number 8 is equivalent to selecting add number 9. And what is the reward for add number 9? You see, it is not closer to what we want. And so the total reward that you get out of add number 9 is in fact 952, which is quite less. So when I adopt a random selection, I am able to select, I'm able to get only 952 as the maximum value. So what is the result telling you? The result is telling you that in the last 1000 iterations, the agent is selecting this particular add number 9 114 times. 112 times it selected this value of 6, which is equivalent to selecting add 7. So let's see what is the add 7. Add 7 is here, and that's about 1112. That's the value that you get out of selecting the add number 7, and the rest is all less. You see, this is the infrequently selected add compared to the rest. Okay. And you see the last add number 10 is also infrequently selected. Okay, so that's the characteristic of the random selection, because it's not doing any learning per se, right? It's exploring wildly, it's exploring with no goal in mind. So of course we expect this kind of a result out of it. Okay, and this shows you the adds that it is selecting in each iteration. It's going haywire. In each iteration, it's selecting randomly, and that's why you have a graph like that. So let's look at the next one, which is of interest to us, which is your Epsilon Greedy. So I'll briefly tell you what that algorithm looks like. It's pretty similar to what we wrote here in the previous one, except for a few additions. One for, you see this exploration and the exploitation. So as I said, this is the loop where exploitation takes place. And this is the loop where exploration takes place. And how do I do it? I control it by using the parameter called epsilon, where I set the value to be 0.1. Okay. And so with that, now we start selecting the add in each iteration. So remember, this np.argmax is going to now select an action that is going to result in the maximum reward. Okay, and the sums of reward is again a list which is going to be updated at end of each iteration, right? So you see here sums of reward is also used here. And so we accumulate that with the rule that I gave you in the slide. Okay, so you see that red colored formula. So that's the same formula which is in use here. Reward minus sum of reward divided by the total number of times a particular add has been selected. Use that to update the sum of reward and store it in the list. Okay, so sums of reward will be a list. Yeah, and that's it. And no other change we require. Let me run this exercise and see what is the result that we are getting. You see, consistently for the last 500 iterations, it's able to select the add number 10, which is equivalent to 9 in the case of our list here. So let's look at the table and look at the reward. What is the total reward here? 2510. We have scored well over the random selection algorithm and beaten it by hand, right? So out of the last 1000 iterations, again, I'm printing the last 1000 iterations alone. Out of the last 1000 iterations, you're able to get a value of 900. I mean, 900 times out of 1000, the agent is selecting the add number 9. That's a very impressive performance, right? And look at all the other ads. They are all quite low, except for the add number 10, which is equivalent to the number 9. All the others are selected less than 100 times. You see add number 8 is getting selected only 16 times. You see 0.06 because I have divided by 1000 because I have normalized it. That's the reason why you see that as a 0.016, 0.9. But essentially, the agent has selected only this particular ad number 8 only 16 times, 14 times, 13 times, pretty less. And these are all, I will tell you, during the exploratory stage. These are all while doing the exploratory stage. So the agent is now able to learn well because it is now using a combination of exploitation and exploration. Remove this exploitation part, you will suffer. Remove this exploration part, you will suffer. Okay, so I will stop here. We are at the close of the session 1. Any quick questions before we part for a break? Okay, so let's break here. Post any questions in the chat box if you may have. We'll resume at around 11:17, exactly 15 minutes from now. Okay, bye.